Okay, good afternoon. All right, so I wanted to, the last couple lectures I feel like I've been sort of like, I don't know, pushing a little bit of material into the next lecture every time. So I want to, so I'll finish up last details about chapter 29 for real, and then I'll start reviewing. So I think I'm going to get done reviewing everything since the midterm. So basically chapter 16 and on. I think I'll finish all that today. If I don't, I'll maybe talk a little bit more about that stuff on Tuesday. So next week, I've said most of this before. I'll just repeat some of it about next week. So next week, Tuesday's lecture will sort of be as usual in the sense, same time, same place, all that. I'll just intend to pretty much answer questions, though. So come with questions, anything you want to know. It will be webcast, so if you can't come for whatever reason, you can look at it online. Sections also will meet as usual on Monday. You can get homeworks back, quizzes back, all that kind of stuff. And as far as like office hours and reviews and things like that, all the GSIs are going to have some kind of review next week as they did for the midterm, and all that information will be on BSpace, hopefully not by the end of today, then tomorrow. And so you can look at that, and obviously you can ask your GSI on Monday what's going to happen with that, that stuff. I think most of them are going to, like they did for the midterm, more or less keep things when their office hours are, but since it's sort of a dead week, they might move things around a little bit if they have other things they want to be doing. My Tuesday office hours will be the same, but I'm going to change my office hours, I think, later in the week. I'm not sure exactly what I'm going to do, but probably I'll probably have them on 2 more hours on Thursday. I'm not quite sure when. I want to coordinate a little bit with the GSIs. Homework solutions for all the homeworks are now posted in the 3rd floor of Evans, so if you want to look at any of that, you can. We're a little bit behind on getting all the quiz solutions kind of in a nice format for you to look at, but I'll put those on BSpace when we do that, just like for the quiz. So quizzes 4, 5, and 6 will have all the solutions up in the next day or two. And I think that's it that I wanted to announce. Oh yeah, so I wanted to say, so I'm going to check, I'll put this in an announcement on BSpace also, but I want to check IDs at the final. I don't know if, I don't think anything's gone wrong in the past, but I think it's just a good, I don't know, just a little safeguard. So bring your ID to the final. And like I say, I'll announce that and remind you, but yeah, bring your ID to the final, and I'll just have GSIs check them when you hand in your exam. Okay, questions? Anything logistical, administrative, anything else? Anything else anyone wants to ask? Okay, so let me just talk, like I said, a little bit about chapter 29, the very end of my discussion of that. So I sort of did a quick explanation of these 2 issues. One of them is the data snooping multiple testing issue, and the other is the one-sided versus two-sided tests. But I wanted to do an actual example. Well, actually, I'm sorry, I want to do one more example of each. Okay, so. So suppose we have 100 researchers, and they all do an experiment to see if a drug will make lab rats live longer. And suppose there's nothing, the experiments are all run well. There's good treatment group, control group, placebo, everything's done well. Okay, so there are no like issues with this experiment, and in fact, so they're all testing the same drug. Okay, so they're all testing the same drug, and in fact, the drug does nothing. So this is equivalent to saying, well, let me say this. Yeah, so this is equivalent to saying that the null hypothesis is true, right? The drug does nothing, so any differences we see between the treatment and control group are just chance, okay? And ask this about how many will reject null at 5% level, concluding that the drug helps, or the drug, when I say helps, I mean that it makes the rats live longer on average. Okay? So anyone want to answer that or ask any questions about it or anything? Yeah. About 5. Any other thoughts? Yeah.
So we don't care about whether or not the drug,
That's right. We don't care about whether or not the drug hurts them. Okay, they're all testing to see whether or not the drug makes them live longer. So this, if you think about the two-sided issue, this would not be a two-sided hypothesis test because we only care about the drug if it actually helps them. So it's only one side. Yeah. Any other questions or thoughts? Okay, so that's right. That's about 5, and it's the same logic as we talked about before with the card guessing example. If 100 people guess at this card game, and in fact they're just completely guessing at random, meaning that the null hypothesis is true, then we expect about 5% of them to get off in this tail where they would falsely conclude that the null should be rejected, or the null isn't true. So the null gives us our expected value in the middle, and it's the same idea that so this area is 5%, and if result is in this shaded area, that means that we would reject the null at the 5% level. Okay, so these people, again, just like we were talking about on Tuesday, these people are making a mistake. These researchers are incorrectly concluding that this drug helps the rats live longer. Okay, so I sort of wanted to, even though this example is sort of basically the same, I wanted to just ask one more question about this, which is, who do you think, out of all these 100 people, who do you think will try to publish their results? What's that? Yeah, so these people are more likely to try to publish their results, right? It's not particularly, like if you got a result that's sort of around here somewhere, it's not very exciting for you to submit a paper to a journal and say, well, I conclude that this drug is indistinguishable from random variation, basically, right? You're saying that I can't conclude that this drug does anything. You're probably not going to submit that for publication. If you get out here, you get a result. And there's a little bit of a, the method of hypothesis testing is one where you want to be a little bit careful about your results for that reason, is that you have to recognize that sometimes these mistakes will be made. And you have to take things with a little bit of a grain of salt because there may be this, I mean, the world is a little bit more complicated than this, but there may be a lot of people doing research, and the ones that get the p-values less than 5% are typically the ones that are going to try to publish. Now, it may be that the drug does actually do something. When you see a result in a journal or something, it may be that it really does do something, but there is this possibility that sometimes there are these mistakes being made, okay? Now, in the world of peer-reviewed science, this will be corrected, right? Someone else will, like one of these 95 people that didn't reject the null will, they're working in the same field, probably some of them will read the journal articles and they'll say, well, I tried the same thing and I didn't get any results. So the research will be kind of compared and maybe some more experiments will be done, and in the end, people should figure it out, right? Figure out that, in fact, it looks like those results out there are, in fact, just due to chance because there are all these other results that are sort of near the null, meaning no effect, okay? So anyway, so in the world of science, since things are peer-reviewed, these mistakes should get sorted out, but first time you see a result, you might take it with a grain of salt because sometimes things do get kind of corrected, You'll have some exciting publication, and then it'll turn out that other people will say, well, doesn't look like that's really true. Okay, so there's that, and I wanted to do one more example of this really quick. Suppose we have one researcher tests for 20 different possible benefits. So same kind of context. There's a drug. The researcher tests for 20 different possible benefits. They might be like this: longer life, lower cholesterol, lower risk of cancer of some sort or another, and all kinds of possible things that might be nice for rats. Okay, maybe it makes some of them lose weight, whatever. You have these possible benefits, and if you have one researcher that takes the data and does 20 different hypothesis tests, either using the same rats or different rats, it really doesn't make that much difference. What do you think will happen in those 20 hypothesis tests? Will any of them be rejected at the 5% level? Yeah. Yeah, so it's about one. It's sort of the same story, that each one of those hypothesis tests, if the drug does absolutely nothing, each one of those hypothesis tests has about a 5% chance of getting out in some tail and being rejected, making the researcher conclude that, okay, reduces the risk of liver cancer or whatever. One of those 20 things. About one of them will typically give you a p-value less than 5%. So this is a little bit more, how should I say, sort of more sketchy. Like these people, these 100 people they're all working by themselves. They're doing their own little experiment. They're not doing anything wrong. This researcher then, if this researcher looks at the data in 20 different ways and then tries to publish the one p-value less than 5%, that's not really fair, right? It's sort of cheating because, if you test for enough things, eventually you're going to get a p-value less than 5%. The rats have to die of something. They have to, maybe they'll live a little bit longer, or slightly fewer of them will have one bad thing or another. Okay, so because if you look at lots of different things without any particular idea ahead of time what you're looking for, it's sort of cheating. You're sort of setting yourself up for rejecting the null when maybe the results are just due to chance. Okay, so this is something that's I think a lot of people do kind of accidentally. People get some data and they think, what's going on with the data? Well, let's look at this. Let's look at this. Let's look at this. Oh, wow, look at that. Got a p-value less than 5%, right? And so there's this tendency to believe after you look at the data, whatever story the data tells you to a certain extent, when in fact, if you look hard enough, if you sort of a little statistician's joke that if you torture the data enough, it will confess. That if you just kind of look at it in lots of different ways, eventually you might find some pattern, right? But, just because of randomness, there's likely to be some way in which the rats have some either positive or negative unusual result. Okay. So, the way to get around this then is to have some idea ahead of time when you design your experiment, okay, this is what I'm testing for. I'm testing for this one thing, and then my p-value is fine. If you want to do something like this, then I won't ask you to know this, but you have to basically adopt a stricter standard, okay? Rather than saying p-value less than 5% in a case like this, you would want to adopt something more strict so that you wouldn't be making this mistake very often, right? So if you only rejected when you had a p-value less than like 1% here, then it will be less likely that you'll accidentally reject the null incorrectly. One quick, dirty fix you can make is if you have 20 different p-values, divide them all by 20, okay? So then you're not going to make this kind of mistake. You're not going to make it any more than 5% of the time, okay? So that will sort of get rid of that mistake. If each p-value is, rather than rejecting the 5% level, if you require it to be less than 1/20th of that, then you won't be making this sort of bad mistake. Okay, so like I said, you don't need to know that, but that's sort of a rough, quick fix you can make is to just adjust where you draw this line essentially. Just draw it farther out, and then you won't be making this mistake so much. Okay, so questions on that stuff? Okay, so this setting is sort of called either data snooping or multiple tests. I sort of think of this example to be an example of multiple tests, and this as an example of data snooping, where you're sort of searching for something and sort of, I don't know, cheating, I guess. Okay, so the other thing I wanted to talk a little bit more about is this two-sided test thing, and I thought I'd do a quick example of it, just to contrast with all the examples I've done before. So everything I've done before has been one-sided, and like in this case, this says to see if the drug will make lab rats live longer. So saying that it's going to make them live longer means that you would only reject the null hypothesis if they actually live longer, right? If they live really short amounts of time, like if your z-value is negative and way off to the left, that's not going to make you conclude they live longer, right? So we don't care about that tail. Okay, so suppose and I said this in English without giving you any numbers. Suppose I wonder if a die is fair. So first of all, as I said on Tuesday, you might think, well, what results would convince me that it's not fair? I'm trying to test this hypothesis and think, okay, I'm going to conclude at the end, either I think it's fair or I don't think it's fair. So if you got results that are either too high or too low, either way you'd be convinced that it's not fair. So that's what makes this different from that, right? Here, we're only going to be convinced in one direction. In my original card guessing example, I would only be convinced that I'm doing better than guessing at random if I actually did better, right? If I actually got more than 20 right, off in the tail somewhere there. And if you look at the examples that I've done and the ones in the book, they're pretty, I know I've been careful, and the book is pretty careful about making sure that the context suggests only one direction, like Botox works, Cal % Democrat is more than Stanford % Democrat, things like that. Okay, so if you don't have any reason to think one way or the other, the question I'm basically asking is or I'll say it this way. Can the data be explained by chance? Or are the results so far from the expected value. I'm being kind of long-winded here because this is my last example, so I want to be a little bit careful about it. Are the results so far from the expected value that chance is not a good explanation? Okay, so that's kind of the fundamental thing that we're always deciding in a hypothesis test is chance a good explanation or not so good an explanation? And again, there's nothing in this question that suggests a result either on one side or the other. Okay, so really, in real life, you should be deciding whether or not you're going to do a one-sided test or a two-sided test before you look at any data, because the data the data is going to be on one side or the other, and that may make you, I don't know, think that that's the tail you want to look at, right? You have to be a little bit careful in thinking, okay, well, would I have rejected on the other side, right? But yeah, so if you decide before you look at the data, then it's a little bit easier to think about, I think, whether or not you want to do one-sided or two-sided. So let's suppose we have 100 die rolls, and the average is 3.2. And I'm going to give you a sample average. So this is a sample average of the die rolls, right? The sample SD, let's say it's 1.5. Okay, so let's do the hypothesis test. What does the null say? The null says it can be explained by chance. And that the die is fair. So when you sort of think nothing's going on is basically saying that this die is fair, and there's nothing wrong with it. Okay. The alternative says that it's not just chance. And that the die is not fair. Okay, so again, when I say die is not fair, that does not imply a direction. All the other examples I've done, somehow the alternative suggests one direction. So whenever you answer a question on the final, you should think, does this imply a one-sided test or a two-sided test? And that should be reflected in this B part of the alternative. Okay? Should also be reflected in your math, in your p-value, but the alternative should agree or sort of be consistent with whatever kind of test you're doing, one-sided or two-sided. Okay, any questions on that? Okay, so then let's do it. The Z So really quick, let's just think about, well, I guess I need to get the SE first. I want to think about whether or not the Z-test is justified. So first of all, there are more than 25 draws, so it looks good. We should think about the other check we need to make, which is taking the expected value plus or minus 2 standard errors, and think about whether or not that's in the range of possible values. You'll see once I do the math it is, so I'll mention that again once I do the SE. So okay, when we do the Z-value, first of all, we set up the box based on the null hypothesis. The null hypothesis says the die is fair, so it looks like this. Okay, we have fair die, 100 draws. Now, according to the null, the average of this box is 3.5. So when we get our Z, it's going to be 3.2 minus 3.5 divided by the SE. What kind of SE will that be? Average, right? This is an average of our sample. This is an average of the box. This should be SE average. So what SD should we use in calculating the SE average? Yeah. Sorry? SD of the box? Anyone agree, disagree? Any thoughts? Questions? So yeah, SD of the box is always what you would like to use, okay? And if you remember, we had this discussion about like which SD should you use. If you know the SD of the box, or if it's implied by the null hypothesis, then use it. If not, then use the sample SD, okay? So the question is, do we know the SD of the box, or is it somehow implied by the null hypothesis? Well, it is. The null hypothesis says the die is fair. Once you have a fair die, this is the box, and I can get the SD of that box directly, right? So SD of box comes out to be 1.7. I won't do the math, but if you just take the SD of those numbers, you get 1.7. Okay, so again, I think the thing you want to remember is if you know the SD of the box for some reason, or if it's implied by the null, and in this case it's implied by the null says die is fair, so I can calculate the SD directly from that fair die, then use it. If I didn't know the SD of the box for some reason, then I would use the SD of the sample, okay? Okay, so let's do the math. So SE sum, square root of 100 times 1.7, 17, and SE average is SE sum divided by the number of draws, so I get 0.17. So now this is 3.2 minus 3.5 over 0.17, which is negative 1.75. All right, so that's my Z. Questions on that part? Okay, so I guess this is a plug for, I don't know, I guess you could still buy the lecture notes. If you feel now that you want to get old notes from the class, I guess you could get them, or for, yeah, I guess this is a plug for, right, this class, and I think that's the class that meets after this one. So, okay, let's see, where was I? Oh yeah, so get the p-value. So Z is minus 1.75. Turns out the area, if you look that up, the area is 91.99, so basically 92%. So what's the p-value going to be? That's about 92% in the middle. 8, two-sided, right? We would reject the null if we got a result higher as well. So when you think about the logic of the p-value, how the p-value is defined, it's the probability of data like we got or more extreme given that the null hypothesis is true. So the null hypothesis is what gives us the expected value. And then when you think about it as a two-sided test, the logic is that basically this value and this value are sort of the same, like in terms of providing evidence for or against the null hypothesis, because they're the same distance away. So if I'd gotten, I guess, 3.8, if I'd gotten the same distance above, I ought to be drawing the same conclusion as if I'm here. So when you say data like I got or more extreme, data like I got really is either one of those. Okay? So that's kind of the logic behind thinking about it as a two-tailed test. So then we add those together, we get 8%. Okay? So p-value is 8%. All right, any questions about that? Okay, so then the conclusion is this is just as usual. Once you get your p-value, we can't reject the null in this case. It's bigger than 5%. So this sort of seems like chance. And the die looks okay. Okay. This is at least consistent with results we might expect from a fair die. It's a little bit off maybe, but not very far off. Okay? Literally, if the die were fair, we should expect results that far or farther about 8% of the time. Okay. So, so I wanted to just mention about doing the normal approximation in general, what justifies it. Well, SE average is 0.17. So if we go 2 standard errors either way from 3.5, there's no problem, right? This is well within the range of possible values. We could get anything from 1 to 6 for an average. So expected value plus or minus 2 SEs is fine. More than 25 draws, fine. So normal approximation makes sense. Okay. Questions? Yeah. You don't have to check whether or not normal approximation is okay. If I'm gonna get you on that issue on the final, I'll make something fail, okay? And then if you don't check it, then you'll miss the problem, right? So I think you should check it, but you don't need to write down, you don't need to write down that you checked it. But yeah, so at some point on the final, when this normal approximation is a pretty big topic, it shouldn't be a surprise that there will be some normal approximation somehow on the final in a few problems. So it's one way I might test you on that is to make one that doesn't work. Okay. Any other questions? Yeah. Yes, Tuesday will be webcast. Yeah. Okay, so I want to make one more thing to just sort of tie these together. Suppose we have a fair die, or suppose 100 people have fair dice, and each person rolls the die 100 times and does a hypothesis test like this one. So what percentage of the people will reject the null? So you might think, thoughts might be 10%, 5%, maybe 2.5%, I don't know. Because there's this kind of, doubling of p-value thing going on. Well, what has to happen in order to reject the null? You have to get a p-value less than 5%, right? Well, how can it happen that you get a p-value less than 5%? Where would you have to be to get a p-value less than 5%? You have to be off to the left here or off to the right here. So what's the total area of these two bits that will give you a p-value less than 5%? Where would it be to get a p-value equal to 5%? If you get a p-value equal to 5%, what's the area of those two bits? Is it 5% or 10%? Yeah, both those two bits together would be 5, right? Because let's say you're right on that line, right? Let's say you're right on the line. Let's say I make those two areas are 5%. If you're right on that line, then your p-value is 5%, right? So the chance of getting either one of these points or more extreme is 5%. And that's exactly what's necessary in order to reject the null at the 5% level. So this does not, doing a one-sided or two-sided test does not contradict or change the stuff that's going on with multiple tests and data snooping. There's a consistent story that if the null hypothesis is true, the chance of rejecting the null at the 5% level is still 5%. Okay, so that statement still is true whether or not you're doing a one-sided or two-sided test. Okay. This does mean that there's a sort of stricter line in the sense that one of these tails is 2.5%, right? So it means that you have to get a little bit farther from the expected value to reject the null if you're doing a two-sided test as compared to a one-sided test. The one-sided test, you just have to get far enough away here to make this tail 5%. With a two-sided test, you need to get a little bit farther to make that area 2.5%, or that area is 2.5%. It's the same total chance of rejecting the null, but you will be a little bit farther away. Okay, so that's I guess that is sort of the reason why you need to decide if you're doing a one-sided test or a two-sided test before you look at the data, is that if you look at the data first and then say, okay, the average is 3.2, oh, I think the die roll is too low, so I'm going to test whether or not the die roll is too low. Okay? That's sort of cheating, because now, by doing a one-sided test, you're making it a little bit easier to reject the null hypothesis. And if you look at the data first and then do a one-sided test, now you'd reject the null 10% of the time if the null is false. If you imagine everyone in the class rolls a fair die, and each person in the class gets their result and then looks at the one-sided p-value, then 5% of the class will be rejecting the null over there, 5% of the class will be rejecting the null over there. So a total of 10% of everybody would be rejecting the null, and that's not right. That's sort of cheating. It's getting around this idea that you should only be making this mistake 5% of the time. Yeah? Yes, the question is when we do the check, are we using the 0.17, the SE average, to make that check? And that's right. Okay, so what I'm curious about is, does the probability histogram for the sample average follow the normal curve? So since it's the sample average that I'm thinking about, I need to use the standard error for the sample average, SE average. Okay? Good. And I'm using the average of the box to make that check, because the average of the box is what's in the center. I want to go 2 SEs either way from there. Sorry? I'm using 3.5. I'm using the expected value because the probability histogram that I'm curious about is this probability histogram. It's centered at this is in standard units or z-values, but in terms of actual averages of die rolls, the center is at 3.5, right? So I want to go 2 SEs from there. Good. Any other questions, thoughts? Okay, so I'm finally done with the book for real. And let's take a little break, and then I'll review back to chapter 16 and on. Okay, so let's get to reviewing. Okay, so things have taken long enough that I'm not going to finish reviewing today, I'm sure, but so I'll do some today and I'll finish the rest on Tuesday. Okay, so starting from chapter 16. Any questions come up for anyone? Anything confusing about the chapter 29 stuff? Okay, so chapter 16. There are kind of two parts to chapter 16. The first part of chapter 16 discusses the law of averages. And at the time, I really just discussed the law of averages for coin tosses. So now I'll go back and I'll describe it a little bit more generally. And it's basically in the context of everything from about here on is in the context of box model. So I'll just describe it in terms of a box model. As the number of draws from a box increases, the results should tend to get farther from the expected value. Tend to get farther from expected value in absolute terms. Okay. So the numerical way that we now see this, at the time we hadn't used SEs at all, but what this is saying is basically the SE sum increases. Okay, the SE sum measures the likely size of the chance error. So when I say tend to get farther from expected value. Another way of saying that is that the chance error tends to be larger, right? Chance error is the distance between the expected value and the observed value. So chance error tends to get larger in absolute terms. And SE sum measures the likely size of the chance error. So that's how we kind of know that numerically. Okay, and then the second part of the law of averages says that, again, as the number of draws increases, we should tend to get closer to expected value for percents and averages. Okay. So this, you think about what we compute to sort of show this, SE percent and SE average get smaller, decrease. Okay, as you increase the number of draws, both of these standard errors get smaller, so the likely size of the chance error for percents or for averages will get smaller. There's another little part of this which says that the chance of getting exactly at the expected value tends to get smaller. So that seems maybe a little bit contradictory. So, however, chance of getting exactly EV gets smaller. And it doesn't matter if you're talking about expected value for the sum of draws, percentage, or average. The chance of hitting the exact center gets smaller basically because there are lots more things that can happen, right? If you have more and more draws, you might be very close to the expected value in terms of the percent or the averages, but actually hitting exactly gets more and more unlikely. And there are a variety of pictures in the book that kind of illustrate that. And I've talked about it a fair amount, so maybe I'll just leave it at that. Any questions about any of this? Yeah? Is the EV like a limit? Well, In a sense, yes. And yeah, maybe I'll be a little bit vague there. There's a sense in which you can think of the expected value as a limit. As you increase the number of draws, you get closer. So yeah, there's a yeah, so you're thinking about convergence in kind of a calculus context, and it's not quite that. So people can ignore me if you want. There's a statistics or probability idea of convergence in probability, which says that the probability of getting close goes to 1. So there is a convergence sense, but it's not as sort of deterministic as you think of as in calculus setting, maybe. So, okay. So that's that. So any other questions about law of averages stuff? Okay. So the second part of chapter 16 introduces the idea of box models. So I gave you these instructions for making a box model. First thing you want to figure out is what numbers go on the tickets. And the way I think about that is to think about what's the quantity I'm interested in. Is it a percent? Is it an average? Is it like a net gain for some gambling problem? What's going on? And what can happen to that thing as I draw more times? So yeah, so So when you do these, you actually have to think about quantity of interest on each draw. So you have to think about the quantity of interest actually as a sum somehow on each draw. Like if you're interested in the percentage of ones, you actually aren't thinking about what can happen to the percentage of ones on each draw. You're thinking about what can happen to the number of ones on each draw, and then you're going to convert that into percentage terms. Okay? So when I say quantity of interest, it's not, if you're doing percentages or averages, you can't think about it directly. You have to think about what would happen to the sum of draws or to the count, and then work from there to the thing you're interested in. So you'll always think about these numbers, I think, in terms of sums or counts. Okay, so there's that, and then how many of each? And I'll just say chances should be right. So if the different things aren't equally likely, then you need to reflect that in the box. So one example of that is like roulette. If the outcomes are either win $1 or lose $1, those might not be equally likely, and so you have to kind of balance things out by having different numbers of winning tickets and losing tickets to reflect that. Okay, so that's that. Make the chances right, and then how many draws. And how many draws is usually pretty obvious. I'll just add on here, now that we've done later chapters, you want to think about whether or not the draws are with or without replacement. Okay? So at the time, we were only doing things with replacement, but now we've also done without replacement, which is a simple random sample. And in that case, you want to at least think about whether or not you should use correction factor. Okay, any questions about setting up box models? Okay, so at this point, hopefully they're pretty second nature. We've been using them for a while now. So then chapter 17 is not very conceptual. It's basically just some math, and so I'll just do that really quick. Hopefully the formulas in here are pretty much second nature to you at this point. There's expected value for the sum of draws, which is the number of draws times the average of box. And SE for the sum of draws is the square root of the number of draws times the SD of the box. And there's this SD shortcut formula. So this shortcut formula is only useful when there are only two kinds of tickets in the box. So there's got to be one of them that's bigger than the other one. So call the big one, and the small one, the small one. And you can do this. Take the big minus the small, and then multiply by the square root of fraction big times fraction small. Okay, so that's that shortcut. And that's basically it. There's a little bit of discussion about kind of different kinds of boxes and whatnot in this chapter, but mostly it's dealt with in the previous chapter. And like I say, I think making boxes hopefully is fairly second nature by now. Okay, questions on that? Okay, so that's 17. 18 deals with probability histograms and normal approximation. So when I did chapter 18, I sort of took a moment, and I guess I'll do that again, to just sort of say there's this relationship between the very beginning of the class and what happens in these chapters, in 17 and 18 in particular, that chapters 3, 4, and 5, chapter 3 does histograms. Chapter 4 does average and SD. And chapter 5 does normal curve. So this is all in the context of like data, lists of numbers. Okay? Now in chapters 17 and 18, we're talking about sums of draws from a box. Okay? I'll just say sum of draws from a box. And that's the sort of general context of what we're talking about. Now, as we go into the later chapters, we're also talking about percents and averages and whatnot. So you can think about this idea more generally, kind of random stuff, whatever you're getting from a box. But there's sort of similar topics going on. So chapter 17 does expected value and standard error, which are very much analogous to average and SD. You can use them to convert into standard units. They basically measure somehow center and spread is sort of how we think about SD. Chance variability or chance error is what's measured by standard error. But in both cases, you're basically talking about how far do you expect to be from the center. Center meaning average here, center meaning expected value here. Okay, so in that way, there's this analogous relationship between those things. But again, this setting is much more concrete. We're really talking about an actual list of numbers somehow, whether it's data or some just list of numbers, possibly tickets in a box. You can find the average and the SD of the box that way. Here, it's a little bit more abstract because you don't really have to have any numbers in front of you. You just have to have a box model. You have to have some context for some random thing that's going on. And from that, you can sort of think about what you would expect to get and how far off you might be. Whereas here, you really actually have some kind of raw data. Okay, so then chapter 18 talks about probability histograms, which is kind of the continuation of chapter 3. But again, for this random context. So a probability histogram doesn't really have anything there. It's all sort of theoretical. It's all based on chance. So each chance represents area for a probability histogram, whereas chance represents just the percentage of the data that happens to be in that class interval for a histogram. Okay, so that's that. And then normal curve has sort of a continuation here. as a normal approximation. So that's also in chapter 18. And there's this story in both situations about the normal curve. If you have data and you know the average and you know the SD and you know the histogram looks like the normal curve, then you can convert to standard units, use the normal table, do all that stuff, right? And similar story here. If you know the expected value in the standard error and you know the probability histogram looks like the normal curve, then you can do normal approximation, which is, again, using the normal, converting to standard units, using the normal curve, doing all that stuff. Okay, so what's going on in these two parts of the book is pretty similar, although, like I say, the context is different. We're talking about something more concrete here, something more abstract here. Okay, so any questions about that kind of big picture stuff, ideas? Okay, so maybe I've said enough about probability histograms. There's a little bit more I want to say about normal approximation, which is just my little rules of thumb. So I said, when you know the average when you know the expected value in standard error and you know the probability histogram looks like the normal curve, well, how do you know? So normal approximation is okay. When, first of all, at least 25 draws. And also expected value plus or minus 2 SEs is in range of possible values. So for this die rolling example I was doing up here, expected value is 3.5 according to the null hypothesis because expected value for the average is 3.5. And if you go 2 SE averages away, that's well within the range of 1 to 6. Smallest possible average of die rolls would be 1. Largest possible average of die rolls would be 6. So since that's well in the range of possible die rolls and you have at least 25 die rolls, normal approximation is fine there. Okay, so that's how to think about that check. Now, later on in the class, when we do confidence intervals, I'll just mention it quickly now, you don't really know the expected value. All you know is the sample value. Right? You don't know the parameter. You don't know what's in the box. That's sort of the point, right? When you're doing a confidence interval, is you don't know what's actually in there. So for that situation, we use the statistic. So I'll just say here, sometimes what the check is to use the statistic, plus or minus 2 SEs. What you really should do is expected value, because what you really care about is the probability histogram for some random thing. And that thing has a probability histogram centered to the expected value. But if you don't know it, this is a reasonable ballpark check. If this is okay, if the statistic plus or minus 2 SEs is okay, then probably the expected value plus or minus 2 SEs is also okay. Okay, questions about that? Okay, so one last thing in chapter 18, which is the continuity correction. Which the book mostly refers to as taking care of endpoints. And what the continuity correction is to go plus or minus 0.5 to get the edges of the bars. Okay, so we should use this when doing normal approximation for a discrete probability histogram. And box contains some consecutive integers. Okay, so this is a somewhat crude check, but what you're actually checking for in kind of real life is you want to make sure that the probability histogram doesn't have any gaps in it. If the probability histogram has gaps, then going plus or minus 0.5 doesn't really make sense because there may or may not be actual edges of bars there, right? So that's the point. And like I said, this is a little bit of a crude check for that, but it pretty much works. So I'll just say no gaps in probability histogram is what we're really looking for there. And I'll just make the comment that if not, essentially what we're doing is pretend it's continuous. Okay, so if the box doesn't contain any consecutive integers, we're essentially pretending that it's continuous, and that's a little bit of a simplification, but I think that's the best, I don't know, fairly easy, consistent story to use for the class. This is a little bit more complicated, but if you just obey this rule and use normal approximation when you have a box with some consecutive integers in it somewhere, and if not, don't. So just use the values themselves, which is like pretending that it's continuous. That's fine. That's sort of right almost all the time. And let's see, some consecutive integers. So for example, I think I gave 129 is an example that's given in the book. So that has some consecutive integers in it, at least 1 and 2 are consecutive, even though 9 is not. So in this case, you would use it. If not, like -1, 1, not consecutive, so you would not use continuity correction for anything with that. Okay, questions on this first one? Okay, so and precise language, meaning that indicating which bars are included. Okay, so precise language indicating which bars are included, like the example in the book is between 45 and 55 heads inclusive, means you include those endpoints. So you would go to the outsides of those bars, the outer edges of those bars. If you said exclusive, you would go to the sort of inside edges. If I said 50 or more, you would use 49.5 because you want to include the bar over 50 and then everything to the right. Yeah, so anything like that where it sort of indicates which bar should be included. And really, for the final, you could stop here. You could just think about this. You don't have to think about precise language. I'll always use precise language if I want you to use the continuity correction. So I might use precise language even when I don't, but certainly if I want you to use it, I'll make sure the language is precise. And the last bit, also you don't really care about, is that it's optional for a very large number of draws. So I said at least 10,000 draws. And basically the issue there is that once you get a really large number of draws, the bars are so skinny that it doesn't really matter if you use the edges of the bars or not. Okay, questions on that? Okay, so that gets us through chapters 16 through 18, and that's a pretty good stopping place. I want to have you evaluate me today, so I want to stop there and give that a chance to happen.